Hi, this is Kevin, and you're watching Google Engineer Explains. Today we're going to be talking about LeetCode 146 LRU cache. Let's dive in. All right. First off, before we talk about this problem too much, let's talk about what a cache is. Okay. And I thought of a good example that can help illustrate what is a cache. So let's say you have, like written an essay in English, but you're in a Spanish class. You have to translate your English essay into Spanish. And so each time you look at a word, you're like, okay, you look at a word, then you get your English and Spanish dictionary out and you translate that English word into Spanish. You have to look it up. But the dictionary is so gigantic, it just takes forever to look up each. Let's say it takes like 30 seconds to look up a word. So every word in your essay, you got to spend 30 seconds, go to the dictionary, look up the new Spanish word, and put it down. It's really slow. So what would you actually end up doing? You'd probably get a little note card and write down some of the words that you use a lot. So let's say maybe the note card fits like 10 words, and you just start putting on the note card some of the words you start seeing a lot. And each time, let's say that word has already happened, the second time you don't need to go into the dictionary because you already put it on your note card. So you just look at your note card really fast, and maybe that takes 5 seconds to just glance at it and put that down as you're translating this essay. So that's essentially a good analogy of what a cache is. The cache is like your note card. It doesn't have all of the words in the Spanish to English dictionary, but it has enough to store some of the most commonly used words, and it's a lot faster to look at the note card than looking up in the dictionary. So basically this analogy, it could be applied to computer stuff like computer data, and maybe you're looking up, instead of English or Spanish words, you're looking up data in memory. Then essentially the note card is your cache, and it's just a smaller subset of the full thing, but it's just faster to get to. So what is a cache? By definition, its behavior allows faster access to specific data, but it has limited capacity, right? You can only write so many words in the note card. Cool. So let's talk about the problem a little bit then. What is this whole LRU business? Well, extending off that note card analogy, let's say your note card can fit 10 items, but as you're writing your essay, you see that, the first 10 words that I put on here aren't actually the most commonly used, and they're not the best words. Maybe as you read more, you can get rid of the items in your note card that aren't really being used that much, or weren't used very recently, and put them with more words that were used more recently. And this way, maybe you're gonna in the note card see more items that actually are in your essay as you're going through, because let's say you can only store 10 items. You want those 10 items to be stuff that would actually be in your essay, so you don't have to keep looking it up. So one way of doing that is you can just go by LRU, which just means okay, the item that was least recently used, we're going to get rid of it and replace that item with a new item for the cache. And each time you look at your note card instead of looking at your dictionary, that's awesome. That's called a cache hit, and it makes things faster. And if we're going with LRU, this is one way to try to maximize the amount of cache hits versus cache misses. LRU isn't the only way to do it, but it is the way that we're implementing for this problem. And again, it just means the item out of all the words you wrote in the note card, the one you used last, if you need to put a new word into the note card, then the one that you used longest time ago will be taken out, and the new word will take its place. Cool. So let's see here. There's a couple functions in here, right? There's going to be the get function, which is basically looking it up from your note card, and that's explained right here. You look at the key, maybe it's the English word, and you get the Spanish word out. So that's going to need to be implemented in constant time. And then you also have put, which is putting something into the note card, which again has to be done in constant time. Cool. And then one other thing is we have a capacity. This is how much items you can put in your note card, for example. So maybe capacity would be, we just have to let's just say like has a finite capacity. So basically, pretty simple. It's like very similar to like the note card analogy. And this right here, this is so this problem actually is different from a lot of other LeetCode problems, in that a lot of the problems are actually you implement some function, and the function is just like within the class. So, but it's really you're just implementing some function. Data goes in, data comes out. For this, you're actually implementing an object. So you can see here how it's called, right? Like you create an object, the LRU cache, which has a capacity set up. Oops. And you can put in a key. You can and you can also put in. You can get the key, and you can put. You can call the get function on the object and put in get a key, get the value out, and you can also call the put method on this object as well and put in a key value pair. So basically, it's like we're making this LRU cache object. We're not like just running some function data through. So this is something like it's more closely related to object-oriented programming. So basically, what we're going to do is going to be implementing a class, more like OOM, right? Instead of like, I guess you could say functional programming for some of the other stuff that is on LeetCode. And so since we're creating a class, the class has some of its own state. Specifically, when we're instantiating, right, the LRU cache, we're saying we're giving its capacity. So it's like each cache has its own specific capacity. So that's just what this is here. Yeah. Anyways, that's what we're doing. It's very similar to like a hash map with getting and putting, but like we also keep track of capacity. Cool. So how will we build this cache? Well, we see this constant time get put. We're talking about key value pairs. Like you should immediately think of hash map data structure, right? Dictionary in Python. This is a data structure that you put in key value pairs, and you can get the value out by you can reference the key. You can give it the key, and you'll get the value out. And both of these operations happen in constant time. So basically, it would cover all of this. Now the twist here is we also need to keep track of what was used more recently. So we need to basically keep track of some type of ordering. Unfortunately, the hash map does not have any ordering associated with it. It's just kind of like a jumble of key value pairs that are, there's no ordering. But we do know some data structures that have ordering. So a few that pop into my mind: arrays and linked lists. And specifically for this problem, there really is only like one like really simple and clean solution that I've seen so far, and this one uses a double linked list. And we'll talk a little bit about why in a second. In the solutions here, there's actually two solutions that they described. I'm going to go through the one with the double linked list and the hash map, which I think is the solution that you will definitely want to use on the interview. They also come up they also describe a solution which is about using an ordered dictionary, and I would definitely not want to do that. You can mention that in an interview, but I would not recommend using that as your primary solution in an interview, because it's just going to, that's not the point of the problem. It's not to say like, hey, I know this data structure that does everything. The interviewer is going to want to see how you like reasoned, how, all the stuff I'm talking about right here, about this constant time gets and puts, the ordering, all this stuff. They want to see you reason all that. So the solution we're going to go with is not going to be like the ordered dictionary one. It's going to be, we're going to use a Python dictionary with a double linked list together. Cool. Let's talk about how we would do this. So we'll have our dictionary, and let's say we have some keys in here. Let's just say we have 3 keys, and each of these key value pairs corresponds to a value. All right, so this is my crappy drawing, character drawing. But basically, like K1 corresponds to V1, K2 corresponds to V2, K3 corresponds to V3. So in the dictionary, we're going to have the key, which is the like K1, K2, K3, and the value is actually going to be a node in a W linked list. So it's hard to illustrate here, but basically this K1, and then it points to V1, K2 points to V2, K3 points to V3. And because we have this W linked list here, we can keep track of the order. So let's say we do something with the cache and we decide to use V3. Well, this is like, let's say the order is like this is the most recently used, this is the least recently used. So if we do something with V3, it has to move to the front. Right now it's at the back of the list. So then we would do something like this. So this becomes 3, this becomes 1, this becomes 2. And that's essentially it. Like each time we touch something in the dictionary, we update the order in our linked list, and we can delete items from our linked list and dictionary together, and we can add things in. And that's basically how we're going to implement this. How we're going to build this cache. So what would happen basically? Actually, let's talk about that in a second. This is going to be our data structure, and let's talk about like why we chose this data structure. So first, like, why these data structures? The doubly, okay, so first off, we need the dictionary because this gives us the constant time get and puts. And then secondly, we would need the doubly linked list, because why would we? Because a doubly linked list allows us to remove, insert nodes in constant time. So what does that mean? Like we can remove a node from anywhere inside this doubly linked list, like V2 for example, just pop it out, and now it's going to be V1 pointing to V3. We can do that in constant time. And we can also insert a node somewhere in here, also done in constant time. So that's why we're choosing these two data structures specifically. Why not array? I mean, let's say you had an array of like 1, 2, 3, 4, 5, right? And you want to put something right here in the middle, like 6. That would essentially require you to move all these other items over by 1, so there's going to be 3 operations to do so. And essentially, like, it just comes out to being like anytime you need to like reorder the array, like insert something in, it basically becomes an end time operation for reordering the array. So it's a lot slower than doubly linked list, or just a linked list in general. Why would we not want to use a singly linked list? It's a little bit more of an implementation detail, but basically, like with doubly linked list, how it works is, let's say you're pointing to V2 and you want to remove this node. Since it's pointing to V1 and V3, you can remove V2 by only having access to that node, and do that in constant time. Whereas if you had a singly linked list, you actually cannot. So let's say you have like A pointing at B, right, pointing at C, and let's say you have access to B and you want to delete B. Well, how do you do that? What you would do is have A's pointer point to C instead, but you can't update A's pointer because from B you can't get to A. So like it's actually not really that ideal for doing so. So basically, cannot delete in constant time without access to the previous node. So that's why I would not use singly linked list. I would not use an array. We need to use a doubly linked list to do all these operations. If this comes up in the interview, I feel like these are going to be important points, so try to remember this stuff. Try to like understand what's happening here. Cool. So let's talk about a little bit about how we would do this. yeah, let's get more into the nitty-gritty of the details. So let's talk about the implementation overview. So there's two things we need to implement: the get and the put. Right? We have this data structure. Like let's start with the get first. This is the easier of the two. So let's say we have get. What would you want to do? Well, first you check if the item is in the cache, right? And that's basically if the item is in this key value pair section. If it's in the cache, this is getting a little cluttered. If it's in the cache, update your list. So you're basically saying, all right, I want to get K3, I want to get K2, I want to get the V2 out. You just need to update your list to say like, well, since I'm touching that item and now it should move to the front, meaning it's gonna, like, let's say I'm touching V3, I want to get V3 out, then V3 moves to the front like this because it's the most recently used, and we need to keep track of the order here of how things were used. So we'll update the list, and 2, we're gonna return the item. Pretty straightforward. And if it's not in the cache, then we're just gonna return -1. So I think that's pretty straightforward. Second part, we would want to do the put operation. This one's a little, slightly more complicated, but not that much more complicated. So we're gonna figure it out. So first, again, if the item is in the cache, then you would want to, again, every time you touch an item that's in the cache, you need to update the list. And this time, instead of returning the item, you're actually putting something in. You're not like taking it out. So we're going to update the value. So this just means like the key value pair already exists in the cache, but you're, let's say the key value pair was like the key was 2 and the value was 2. Now you're saying like, okay, I'm going to update it. Like now key of 2 should point to value of 3. So we need to update the value as well. And if it's not in the cache, we need to first check if like we're at the max capacity. And that's because like we're gonna basically be putting something in, but if we're at the max capacity, we also have to delete something. So in this previous part, if the item is already in the cache, we're not going to need to delete anything, so we don't really need to check the capacity. But if we are going to delete something, if the cache is already full, we have to delete something, then we have to check if we're at the point where we have to delete something. So we would do that. If we're at max capacity, we're going to remove the last item, and we're going to update our hash map, update our list, right? Remove the last item from the list, and we'll take the last item off here, and we're going to add a new item to the front of the list, and we're going to also update our hash map to point to it, our dictionary. Actually, let's call it dictionary. Let's be consistent. And if it's not at max capacity, we're basically just going to be adding the item in. So again, we would just update our list. So actually, these two are going to happen regardless. So it's going to be like this. We'll remove the last item, and then we're going to update dictionary, update our list regardless. Remove last item from our dictionary as well. So this would be with new item. With new item, like that. Cool. All right. So that's basically it. Why don't we do the implementation? So I'm just going to paste some of these notes down into the bottom part there. And let's talk through it as we go through. I know this might still be kind of high level. So let's talk through it as we do the implementation. Hopefully it'll become more clear. All right. First off, we only have the LRU cache object right now, so we also need to define our node object. So let's start with that. This is going to be our doubly linked list node. So it's just basically going to be storing a few different data points. First, we're going to have a key. I'm going to give it a default value, left node, and right node. And this is just saying, like, I'm giving it these default values. Just means, like, if you create this node but don't give it a key or value or whatever, it's going to default to this none value. So self.key equals key, self.value equals value, self.left equals left, self.right equals right. Why do we need both left and right pointers for the node? Because it's doubly linked list, you need to point to the node that's to the left of it and also to the node to the right of it. Or like, so in this example, right, like each node points to the one to the left, the previous node, and to the right, which is the next node in the list. And we're just keeping track of the key value pair here. Earlier we showed that like the key is going to be in the dictionary and the value is going to be the node itself, and the value is actually going to be. So do we actually need the key in the node? We actually do, and that's later when we delete items out from. Like let's say we're removing the last item, we need to know what the key is, so we can not only delete it from the linked list, but we'll also delete it from the dictionary. And I'll talk about that in a little bit as we do the implementation. Cool. So we've got our node, and let's go ahead and let's define some of the state we're going to use in here as well. Well, first we're definitely going to have capacity. And then we're going to have our dictionary. Let's call it a short thing. Our library. We're going to have this is going to be the head of our doubly linked list, which is going to use a node. I'm not going to put anything in it. Self.head and tail are going to be our node, kind of like the ends, which this is going to help us later when we. I'll explain later, but basically this is going to be like a data structure to hold all of our other nodes in it. Basically, since these are right now our linked list has nothing in it besides the head and the tail. The head and the tail need to point to each other. So self.head.right, right? The node to the right of the head should equal self.tail, and self.tail.left. The node to the left of the tail should be the head. Oops. Self.head. So just connecting up this initial things there. Cool. Next, let's move on to the get. Oh, actually, before we dive into that, we need to implement a few helper functions that are going to be used. Right here, I just kind of said like very high level, update the list, return the item, remove the item from the list, remove item from dictionary, whatever, insert item, update our list, right? There's going to be two methods what we really need, so I'm just going to go ahead and put these down. The first one is going to be remove node, and just given a node, and this is the great thing about doubly linked list, you just need to give it the node and it can remove itself from the node. So let me just do the implementation. Node, well actually let's do an example. So just show real quick. A, B, C. Okay, so let's say we want to remove node B. A has a pointer into B. So if you're going to remove node B, basically what you need to do is the A's right pointer needs to point to C, and C's left pointer needs to point to A. And since B has a pointer to both A and C, it's very easy to do this. And this is also why we need to use a doubly linked list, because we can remove a node just by giving the node itself, whereas a singly linked list, you would need access to node A in order to remove node B. All right, so I'll just show. Let me do the implementation. Maybe it'll become more clear like that. So you give them the node dot right, which is node C, right? Dot left. The pointer from C to the previous node to the left node should be equal to node A, which is node.left. And very similarly, node.left.right, which is the node.left is A, and the right pointer of that should point to node C, which is node.right. Okay? So that's how it should be. This also explains why we need to have the head and the tail, because in order for this to work, we basically need to have this node cannot be at the end, because if we say node.right and node.right is like, an empty pointer, then .left is going to give us an error. So basically, if we have head and tail on the ends, then we know that we're only going to be removing nodes in the middle, and we're never going to run into this error because there's always going to be that head and tail buffers on both sides. That's why we maintain that. All right, and then now we're going to do, this is our first helper method, remove node, and then we're also going to do insert after. And this is going to be basically inserting our node after its previous node. Okay. And this is basically going to be used for like getting a new node and inserting it after the head, essentially, right? Whenever we have to reorder our list, we're going to be putting things from anywhere in it to the front of the list. So we're just going to be inserting it after the head. So this will be implemented as such. If you're inserting a node somewhere inside of a linked list, what you need to do is first you need to connect the node. So let's say it's like this, A, and it's already pointing to C. If you want to put a new node B to go in between these, then you would say node.left. First you need to connect the pointers on the node you're inserting. So node.left equals previous, right? So to the left of the node, it should be A. And then node.right should equal previous.right. So previous is A, previous.right is C. You're just connecting up the nodes, the pointers for the node itself. And then right now A is still pointing to C and C is still pointing to A, so we also just need to update those. So you can just say node.left, which is A now, .right, which it was pointing to C, it should now point to the node itself, and then node.right, which is C, .left, it should point to the node. All right. So that's basically remove node and insert node. When you talk to the interviewer about this, these are pretty fundamental functions. Try to get, you want to get these right. Even if you miss something though, usually in the interview, they're not going to like run the code, so it doesn't really matter. It's more about your explanation. Make sure you get the explanation right. The remove node allows you to remove a node somewhere in the middle of a W linked list. It can't be at the ends, and that's why we have the head and tail nodes. And then for this one, inserting after, again, just allows you to insert somewhere in the middle of the list in constant time. And with W linked lists, we're just connecting up all the different pointers. Cool. So we have these two helper functions that we're going to use in the rest of our method here. And also, I just started each of these methods with an underscore. I just saw online that the convention for Python is starting with an underscore means like a private method. That just means like from the perspective of like, if you're calling this LRU cache object, you're not going to call .remove node. This is only going to be accessible to other methods like the put and get methods that are within this object. So that's why I created this underscore thing. All right. And you could talk about that in the interview as well. This basically allows you to do something called encapsulation, which is a big benefit of using OOP, object-oriented programming. Basically, it just means like these like kind of implementation details are abstracted away, and the methods that are exposed do not have access to these private methods. All right, cool. So we're getting there. We have these two helper methods. We've got our initializer set up. So we just need to set up our get and our put, which is we've already written some pseudocode as well. If you've gotten this far in the interview, I feel like you're going to be doing pretty well. Here's the tricky part: is now we have to do this implementation and just get it right. It's very easy to make a mistake in this part. But I think understanding and capturing the conceptually what's happening and showing that to the interviewer is already like doing pretty good. But let's try to do the full implementation here and just see if it works. But I think like again, like even using the pseudocode and like kind of replacing it line by line could help. As I've done this problem to prepare for this video, I've found that it's very easy to make like a small mistake while you're doing the implementation. So just be careful. All right, let's do it. I already written the pseudocode. Let's just start updating the pseudocode with real code. All right, so let's start with the get. We're just gonna, so if the key is in your, what is it called? Self.lib. Just saying like, if the key is in lib, that means that this key is already in our cache. If that's the case, all we need to do is first we're going to update the list. So first we're going to grab that node then, right? So node equals self.lib of key, and it's going to be somewhere in our linked list. We don't know exactly where, but we basically need to move it to the front because it's most recently being touched. So first we're going to remove that node, and then we're going to move it to the front. Right, we're inserting the node right after the head node. And then we're going to return the node's value. Okay, simple. And if our key is not in our cache already, then we just return -1. That's just like part of the definition of the problem. All right, cool. So we basically just implemented this part. That's pretty straightforward, pretty easy. Nice. All right, next, we're gonna do the put part. So again, if item's in the cache, then we're going to first update the list. So that's pretty much the same, right? We're gonna get the node, which is the key value pair in our library. The node is the value. We get that node, we remove it from wherever it is, we insert it to the front. And then now instead of returning the node's value, we're just going to be updating the value. So we'll just say node.value equals value. Right? That's basically like saying we already have some key value pair in our cache, but we're writing in a new value into it. So we have this node.value is this new value. Okay. And we can return here if this is the case. Otherwise, if the key is not in the library, then we have to, now it becomes, we get a few more corner cases. First we have to check if we're at max capacity. So like so how do we do that? How do we know how many items are in our cache right now? We don't have a variable for it, but that's okay because the library only contains key value pairs of items that are in our cache, and we can, in constant time, get the length of our library. That's one thing that the doubly linked list is not that great for. You can't really tell how many items are in the list, but the Python dictionary has this. We can just do if length. This is how many items we have is equal to the capacity. That means we're at full capacity, right? So if we're in this case, we have to first remove the last item from the list. So we'll first grab that last item, which is good thing we have this tail thing, right? So it's the one to the left of the tail is the last item, and I'm just gonna call it the remove node, or the remove, and we're gonna remove this guy. So we'll do self remove node of remove, and then we're gonna also just delete it from the dictionary. So delete remove.key. And this is why we also need to store the key in our node, right? We also need the key here because we want to delete the last item, but we don't know what the key is for that last item if we only had stored the value. So it's important to have also stored the key here. All right, so basically what this does is removes that last item from the end of the doubly linked list and removes it from the Python dictionary. All right. And now we just need to implement this last part, update our dictionary with a new item. So basically add our new item in. So it's actually, we need to like create a new entry now for this. So basically we'll say our new node is equal to node with key and value. and then we're going to insert this right after the head node, right? So basically the front of our doubly linked list. So insert after head, and we're going to take that node we just made and put it after the head, and then we're also just going to update our dictionary. So key, oops, equals node. All right, let me just delete all this stuff. All right, so basically this bottom part's just implementing this last part. Update dictionary with new item, right? That's right here. We added it in. Update our list. We inserted the item to the second item of the list. So just delete all this stuff right here. And that should be it. Cool. At this point in the interview, you probably want to go through some corner cases and just walk through the code a little bit more. And I will do that in a second. But I think we did explain pretty clearly what was going on as we were going through. So I'm just going to go ahead and just try running this and see if we get this to work. All right, cool. It worked. All right, so at this point, let's talk about some corner cases. I think let's start with capacity equals 1, I think might be interesting. Yeah, I was just taking a look at the constraints here. You can't have capacity of 0, which would be actually a very interesting corner case, but that's not part of this. So you could definitely say, like, okay, what is the minimum capacity? If the capacity was 0, we would probably just need to so what would happen if the capacity was 0, actually? Let's start with that. The interviewer could, definitely pose that question. Basically, we wouldn't want to maintain any linked list nodes besides head and tail. We wouldn't ever have anything in our Python, in our lib either. So this one, key and self.lib, is always going to return false, and it's always going to return -1, and that's correct. And then here, if we had 0 capacity, key would never be in here. If lang self.lib equals self.capacity, I think we just need to have one more conditional statement here that says, like, oh, if capacity equals 0, then, like, basically do nothing. Yeah, I guess it's not a perfect solution, but yeah, it would probably just be a conditional right in here for that. And then let's just check if capacity 1 works. Capacity 1 would have one at most would have at most one item in our doubly linked list. So these both would be valid use cases. If there was one item in there, then we would basically just return the value. We'd remove the node from exactly where it is and then insert it right back where it was, and that's still those would work fine. If we're putting something in, if it's in there, that just means that we're removing from where it is, we're inserting it right back where it is, and just updating its value, so that's fine. And then for this one, if it's at capacity, it's basically you're putting in the new item. You're going to remove the one item and then remove it from the dictionary as well, and then insert this new item after the head. So that also looks fine. So yeah, basically it works for those two capacity cases. If you had time in the interview, I know we've done a lot of talking for this problem, so you might not have time. But if you do have time, also what couldn't hurt to illustrate, what the linked list and key value mappings might look like over time as you give them different values. Like you could actually try some of this stuff out and show what that looks like. I'm not going to do it because this video is getting really long. Let's quickly just also talk about time and space. So time, well, it's already part of the definition of the problem. We're going to have a constant time, get and put, and space. This is a little more interesting. And the reason why this is the case is like we're basically doing a bunch of constant operations. The remove node and insert after node. Insert after helper functions are also have a finite amount of things that don't depend on the number of items in the list or anything like that. So they're constant time operations, which is the huge benefit of the doubly linked list. In terms of space, we are going to have it's basically n, and that's basically because we have one key value pair for each item in the cache. For each item in the cache, we're going to have one key value pair in the Python dictionary and one node in the doubly linked list. So it's going to just basically scale with however many items you have. So yeah, that's pretty. Also, more straightforward item there. Cool. So that's basically how you do this problem. I think the meat of it really is like how you're picking these data structures. I mean, definitely talk about why not to use singly linked list, why not to use arrays, and just also knowing how these data structures work together. That's a big part of it. Hopefully you got some value out of this video, and yeah, good luck on those interviews. Thanks so much.